Hello, I am R. Bharandiaran. In this lecture, we will learn how to design a connecting rod. Connecting rod is an intermediate member between the piston and the crankshaft. The primary function of a connecting rod is to convert the reciprocating motion into the rotary motion. The basic most general form of connecting rod and the basic geometry of connecting rod is shown in figure. In the figure, you can clearly see there are two ends, one is called as small end, the other one is called as big end. The small end we otherwise call it as I. This is connected to the piston using a piston pin, whereas the big end is like a split end where the splitted cap is joined by using a bolt, and this end is connected to the crankshaft using a crank pin. The cross section of the connecting rod is I section is shown in figure, whereas the shape of the cross section will vary with respect to the speed of the engine, because the cross section decides the moment of inertia, where the moment of inertia we know already. Moment of inertia is a resistance to a bending. Hence, if we need more resistance to a bending, then we require appropriate cross section. So, most general cross sections are I cross section, H cross section, and for a low speed engine we can also go for a elliptical cross section. The bending direction is shown in the other figure, where it is shown through a arrow mark. Apart from this, we have another one important criteria, that is the length of the connecting rod. Though the length of connecting rod is not directly influencing the stroke of the piston, because stroke of the piston depends on the crank length, whereas the connecting rod length to the ratio, that R, radius of the connecting rod, this L by R ratio, if you increase the ratio or if you decrease the ratio, this affects the side thrust or the side loading on the cylinder. If you decrease the connecting rod length, the ratio obviously decreases, that is L by R ratio will decrease. Because of that, the angularity of connecting rod or motion of a connecting rod increased. Because of that, the more side loading, more thrust acts on the cylinder, whereas if you increase the length of the connecting rod, you can reduce the side thrust. Hence, we have to have an appropriate length. If you increase more, then the buckling also may come into picture. So, most preferred ratio of L by R is 4 to 5, or less than 4. So, this is most general and preferred ratio. For a very high speed engine, we go for a less than 4 or 4 to 5. There are various forces acting on the connecting rod. First and major force is force due to piston. The force transferred on the pistons are gas pressure force and force due to inertia of the reciprocating parts. So, this net force acts on the piston, and thus that force will be transferred to the connecting rod through a piston pin. Apart from that, there are another one force, that is force due to inertia of the connecting rod or a inertia bending force. Apart from these two major forces, there are other minor forces, that is force due to friction of a piston rings and of the piston, and force due to friction of the piston pin bearing and the crank pin bearing. Since this is an elementary level course, we are not considering the frictional forces, that is forces mentioned in third and fourth. So, only in this course for designing a connecting rod, we are going to consider only the first two forces, that is forces on the piston and forces due to inertia of the connecting rod. When we discuss detailedly forces on the pistons, if you see the figure, the forces on the piston are Fp. The net force on the piston is Fp. This Fp is not simply a gas pressure force, it is also the force of inertia, inertial force and weight of the piston. So, Fp is a net force on the piston, and when the piston is with the cylinder, so you will be having a normal reaction force Fn, and these Fp and Fn is converted, or the force is transmitted to the crankshaft through connecting rod. So, hence the force acts on the connecting rod is Fc. If you plot a vector diagram, then the force diagram will look in the next figure, that is Fp and Fn. Fp is vertical and Fn is horizontal. So, the net force acts, or the force transmitted to the crankshaft through connecting rod is Fc. The second force, force due to inertia of the connecting rod. So, here force due to inertia of the connecting rod or inertia bending force is because of the motion, of the connecting rod. So, here whatever the forces, whatever the stresses induced on the connecting rod is called as whipping stress, because the action is like a whipping action. This actually is nothing but a bending stress. The motion whatever happens is a bending, and whatever the stress is induced is a bending stress, but in this case it is because of whipping action. We call this stress as whipping stress. From piston pin to crank pin, that is mentioned as P and C, where C will have more, at C we will be having the maximum reciprocating forces, because where it have maximum acceleration when it compared to point P. Then third and fourth, the forces due to friction of piston rings and of the piston. This is usually very small. For this course, this is not necessary. Similarly, force due to friction of the piston pin, bearing and crank pin bearing, that is also comparatively less, and it increases the compressive stress on the connecting rod. So, still we are not considering in this course. Comparative to first two forces, these third and fourth are small. So, in the design of connecting rod, we have 4 different parts. So, we are not looking into all the points, we are most general and outline of connecting rod. If you discuss the major parts on the connecting rod, or major parts of the connecting rod are dimensions of the cross section of the connecting rod, where we decide the cross section like elliptical cross section or I cross section or H cross section or any other special cross section, that we will decide. The second one is dimension of a crank pin at a big end bearing and piston pin at a small end. Then size of the bolts for securing the big end cap, because in the crankshaft, in the big end, it is a split type. Hence, you have a cap, and this cap is secured by using a bolt. So, that bolt need to be designed, and then the thickness of the big end cap. The first one, that is cross section of the connecting rod. Cross section of the connecting rod is decides the moment of inertia. Hence, moment of inertia is a resistant to a bending. So, here bending must be avoided, means here bending this occurs because of if the length of the connecting rod increases, buckling may occur. So, to avoid buckling, we have to choose a right cross section. So, buckling load is the load acts which bend the connecting rod. Hence, take a buckling load equation, that is Rankine's formula, whereas WB equal to sigma c a by 1 plus a into L by kxx into kxx square, where here L is the equivalent length of the connecting rod, that is length between center of the small end to the center of the big end, and A is a constant which is based on the materials. And another one important information that is the cross section. When we choose the cross section in this lecture, we choose x-axis where it depends on with respect to that rotation. The rotation occurs with respect to x-axis. Hence, the moment of inertia with respect to x-axis axis must be more compared to y-y axis. That is clearly shown in the figure. The x-axis axis is the axis with respect to that the connecting rod bends. Hence, the moment of inertia with respect to x-axis must be more than the y-y. Then second important parts are crank pin and piston pin. We know that the gas force is transmitted to the piston pin, then that is to the connecting rod, then that is to the crankshaft using a crank pin. So, the force acts on the crank pin is maximum gas force, that is FL. Hence, this FL must be withstand by the crank pin. The design must withstand the gas force. The crank pin is connected using a bearing. So, whatever the load acting on the crank pin is bearing load. So, the bearing load must be equal to the gas force. We can consider a factor of safety later, but the bearing load must be equated to the maximum gas force. So, here maximum gas force we can calculate from the gas pressure, whereas this consider a circular piston, whereas the area is pi by 4 d square into p, where d, capital D is the diameter of the piston and p is a pressure acts on the piston, which is equal to PBC into LC into DC. This is a bearing load where PBC is a pressure on the crank, allowable pressure on the crank pin, and LC/DC is a projected area. So, LC is length of the crank pin and DC is the diameter of the crank pin. In general, we assume LC equal to 1.3 DC. Then second, we have to design the piston pin. Again, the piston pin transmit the same gas force to the transmit the gas force from the piston to the connecting rod. Hence, here also we have to design a piston pin with respect to gas force. So, here gas force pi by 4 d square into p, which is equal to pressure, allowable pressure on the piston pin into projected area. So, here projected area is LP into DP. This LP is length of the piston pin and DP is the diameter of the piston pin, and generally we assume that LP equal to 2 into DP. When it comes to a design of bolts, so on the bolt how the load is acting. So, in the cap, the load acts on the cap is a inertial force due to reciprocating parts. So, inertial force, how we calculate? Inertial force we calculate as mass into acceleration. So, here whatever the force acts on the bolt is inertial force. So, inertial force is equal to mass into acceleration. In the mechanics of machines or kinematics of machinery, already we studied what is acceleration on the connecting rod, that is omega square r into cos theta plus cos 2 theta by L by r. That is inertial force is mass into acceleration. So, acceleration is r omega square into cos theta plus cos 2 theta by L by r, because acceleration varies with respect to theta. Now, here the bolt, the load acting on the bolt through cap is a tension force. Through cap is a tension force. Hence, the tensile load we have to consider, that is, we have to equate the tensile load to the initial force of the reciprocating parts. Now, initial load, tensile load on the bolt is sigma T into pi by 4 dCb square into NB. Here NB is the number of bolts, NB is the number of bolts, and dCb is the core diameter of the bolts. Because when it breaks in the core diameter. Hence, the amount of load it can take is by the core diameter. Hence, from the core diameter, we always express the bolt in terms of nominal diameter. So, we have to determine what is the nominal diameter of the bolts. The nominal diameter of the bolt dB equal to dCb by 0.84. Then fourth one, the thickness of the end cap, big end cap. Here the load acts on the big end cap, we can consider as like two different cases. One is it's a simply supported beam with a concentrated load, and simply supported beam with a uniformly distributed load, whereas we have maximum bending moment as Fi into x by 8, and for a concentrated load Fi x by 4. Now, take an average of it, we get the maximum bending moment on the big end cap is Fi x by 6, whereas this x is the distance between the bolt centers, and Fi is inertial force, because that is what acting on the big end cap. Then from there, bending moment, bending stress we have to calculate. So, sigma b equal to mc by zc. Zc is a section modulus. We take a rectangular cross section, hence the zc become bc tc square by 6. So, here sigma b becomes mc by zc equal to Fix by 6 into 6 by bc into tc square. So, considering maximum bending stress of material, we can calculate the Tc, that is thickness of the cap. Now, we will discuss one example problem so that we can understand how to design the connecting rod. So, as a steps, the four geometry we have to design. First one, we have to design the cross section of the connecting rod. Then we have to design the crank pin and piston pin. We have to design the crank pin and piston pin. Then we have to design the bolt which secures the big end cap. Then we have to design the big end cap thickness. So, these are the four geometry we have to design. The load acts on the connecting rod, four loads. Forces due to friction we are neglecting here because of this is elementary level course. We consider only two forces. One is forces due to gas pressure, and then initial force due to reciprocating parts. Forces due to gas pressure which influences the design of cross section of the connecting rod, and then the crank pin and piston pin, whereas the forces due to initial force influence the bolt design and thickness of the cap. Now, in this problem, we have to design a connecting rod for an IC engine running at 1800 RPM and developing a maximum pressure of 3.15 Newton per mm square. So, speed is given and maximum pressure is given. The diameter of the piston is 100 mm. Diameter of the piston is given as 100 mm. So, from here we can calculate the force, gas force. Then mass of the reciprocating parts per cylinder is given, and length of the connecting rod 380 mm, stroke of the piston 190 mm. If the stroke of the piston is 190 mm, then crack length is half of it. And compression ratio is 6:1. So, this compression ratio is a surplus data, we do not require to solve the problem. And take a factor of safety of 6 for the design. Take length to diameter ratio for a big end bearing as 1.3, that is LC equal to 1.3 DC, and small end bearing as 2, that is LP equal to 2P, and corresponding bearing pressure as 10 Newton per mm square and 15 Newton per mm square. The density of material of the rod may be taken as 8000 kg per meter cube, and allowable stress in the bolts as 60 Newton per mm square and in cap as 80 Newton per mm square. The rod is to be of I section, for which you can choose your own proportion. Draw a neat dimensioned sketch showing provision for lubrication. Use Rankine formula, for which the numerator constant may be taken as 320 Newton per mm square and the denominator constant 1 by 7500, that is sigma c is 320 Newton per mm square and A is 1 by 7500. So, first step, we have to design the I section of the connecting rod. So, before we begin, we have shown what is how the I section will look like. So, the I section thickness is considered as T. In terms of thickness, we refer the height of the I, that is h equal to 5t, and breadth of the I is taken as 4t. And the axis is also clearly mentioned. The axis, horizontal axis for this I section is xx and vertical axis is yy. We also said previously that xx, with respect to xx, the moment of inertia must be more, because that is the one which has to resist bending, because that is the direction where the motion is occurring. Now, in general, the most preferred cases, the Ixx must be equal to 4Iyy, or Ixx by Iyy must be less than 4 also is fine. The length of the L by R ratio, or the moment of inertia, that Ixx by Iyy ratio must be less than 4. If it is more than 4, it is used for a very high speed engine. If it is very less, then the angularity is increased. So, Ixx must be equal to or less than 4. Ixx by Iyy must be less than 4. So, area of the cross section in terms of T, if you calculate, so 2 into 4T into T plus 3 into T equal to 11T square, whereas Ixx, in the previous slide, you go to Ixx. So, when you calculate Ixx, so for this rectangle, this rectangle, this rectangle, if you divide in this manner, then you have to use a parallel axis theorem to find the moment of inertia. Whereas, you can also assume this whole thing as a bigger rectangle and this as a smaller rectangle. Whereas, all the 3 rectangles, or if you take this whole thing as one rectangle and this as a second rectangle, these 2 rectangles have the same centroidal axis as Ixx. Hence, you can use the formula directly. So, Ixx is 1 by 12 B into T cube, B T cube or BH cube by 12, BH cube by 12. So, where here B is 4T and H is 5T. So, BH cube by 12 is 4T into 5T cube, and minus of this portion. This portion is, if you leave this distance T, then this total distance is 3T and this height is again 3T. Hence, minus of 3t into 3t cube. You will get 419 by 12 into t power 4. Whereas Iyy you can calculate. In the case of Iyy, if you divide this into one rectangle, second rectangle and third rectangle, for all these three rectangles, the centroidal of axis of these three rectangles is same as yy. Hence, directly you can use the formula of same b cube h by 12. So, here b is, for this rectangle, b is 40 and h is t. So, for this b is t, h is 3t. So, hence Iyy will become 2 into, that is 2 rectangle, that is b h cube, t into 4t cube by 12 plus 1 by 12, b is 3t into h is t cube. So, 1 by 12 3t into t cube, which is equal to 131 by 12 into t power 4. Now, if you divide this Ixx by Iyy, t power 4 and t power 4 will get cancelled. Finally, you will get the ratio, that is 3.2. Now, the 3.2 is lesser than 4, hence it is satisfactory. So, whatever the proportion we initially assume, that is breadth as 5t and height as 4t, that is fine, that is satisfactory. Now, we have to go for finding the thickness of the I cross section. Now, we have to calculate the load acting on the gas piston, that is Fc equal to Fl equal to the area of the piston, because diameter is given as capital D is given as 100 and pressure acts on the piston is given as P, that is 3.15. Now, Fl equal to pi d square by 4 into P, you will get 24740 Newton. Now, factor of safety is 6, hence Wb equal to Fc into Fs. You can calculate the factor of safety, like you can include the factor of safety by multiplying the force or by dividing the stress. So, either way you can consider. So, here we took Wb equal to Fc, that is force due to gas pressure, into factor of safety 6. So, we get 148,440 Newton. We know now the radius of gyration, because the Rankine's formula is Wb equal to sigma c A by 1 plus A L by Kxx square. So, we know Wb now, we calculated, sigma c is given in the question as a constant and A also given in the question as a constant, and area already we know, we have calculated for I section, that is 11t square, and length, that is equivalent length, that is also given in the question. Now, Kxx, radius of gyration, we have to calculate. So, Kxx is nothing but root of Ixx by A. Ixx already we have calculated in terms of t. So, 419 t power 4 by 12 into 1 by 11 t square, that is area. Now, you will get 1.78 t. Kxx is 1.78 t. Now, substitute these formulas over here. Once you substitute, you will get an equation as t power 4 minus 42.2 t square minus 257.3 equal to 0. From here, we can calculate t as 6.9. So, you can round off it as 7 mm. Thus, the dimension of I section of the connecting rod or thickness of the flange or web section. From T, you can calculate what is B and what is H. So, B is 4 times of T, so 28 mm, H is 5 times of T, hence 35 mm. This web section will not be uniform throughout the length. It is bigger near the big end and smaller near the smaller end. So, we have a ratio how it varies. So, near the big end, H1 equal to 1.2 H, that is 1.2 into 35 mm, you will get 42 mm. Where at small end, H2 equal to 0.85 H, which is equal to 0.85 into 35 equal to 29.75, say 30 mm. Then the other dimension, that is B, so let us call it as B1, which is equal to 42 mm into 28 mm. So dimensions of the section near the big end is 42 mm into 28 mm, near the small end is 30 mm into 28 mm. Now the sharp corners, mostly we do filleting, other kind of finishing work we can do it. Then the second one, we have to design the crank pin and piston pin. Already we discussed the crank pin and piston pin will have a bearing stress. Hence the bearing load must be equated to the load which is transferred from the piston. So here the load transferred from the piston is gas pressure force. So gas pressure force we already calculated, that is 24740 Newton. Now we have to calculate what is the bearing load. So bearing load is nothing but bearing pressure into projected area. So bearing pressure for the crank pin is PBC multiplied by projected area is LCDC. Now if you substitute LC in terms of DC, that is LC equal to 1.3 DC, if you substitute you will get 13 DC square, and bearing pressure PBC is given in the problem as 10 Newton per mm square. Hence bearing load is calculated for the crank pin as 13 DC square. Now equate this to the gas pressure, gas force. So here maximum gas force is 24740 Newton. So from here you can calculate the diameter of the crank pin DC as 43.6, say 44 mm. From here you can also calculate the length of the crank pin, that is 58 mm. Now calculate the piston pin. So piston pin, again the load acting on the piston pin is a bearing load. Hence bearing load must be equated to the maximum gas force. Now again maximum gas force we already calculated, and bearing load on the piston is projected area into the bearing pressure. So bearing pressure value is given as 15 Newton per mm square for the piston pin multiplied with dP LP. So here LP is given as 2 times of dP. Substitute that, you will get bearing load as 30 times of dP square. Now by equating to maximum gas force, we can get diameter of the piston pin as 28.7 mm. So you can say 29 mm, and length of the piston pin is 2 times of dP. So each is equal to 58 mm. The third geometry is size of the bolts. So size of the bolts, already we said, on the bolt the load is the load acts on the bolt is inertial force or inertial load due to reciprocating parts. This inertial force due to reciprocating parts will induce a tensile stress in the bolt. So hence tensile load must be equated to the inertial force of the reciprocating parts. So tensile load for the bolt is simply area into stress. So here area is pi by 4 dCb square. So here dCb is the core diameter. So core diameter of the bolt. So pi by 4 dCb square into sigma t multiplied by number of bolts. If you use 2, so put 2. If you use 4, use 4. So mostly 2 bolts are used. So we put number of bolt as 2. Now calculate the inertial force due to reciprocating part, that is m into a, mass into acceleration. This acceleration we know from the basics. Acceleration on the connecting rod is w square r into cos theta plus cos 2 theta by L by R. The maximum load transferred through piston on the connecting rod is at when theta equal to 0 or when it is equal to 180 degree. So, that is the point where the exact push and pull force is happening, which is maximum compared to other points. Hence, consider theta equal to 0. So, substitute the theta value as 0. Now, Fi is mr omega square into r 1 plus r by L. We know already r, that is crank crank length, that is r, divided by L is the equivalent length of the connecting rod, that is 380 mm. So, substitute the value, you will get Fi as 9490 Newton. So, equating this inertial force to the tensile load of the bolt. So, tensile load already we calculated as 94.26 into dCb square. So, equate this to 9490 Newton. Now, from here we can calculate dCb as 10.03 mm. Now, this is the core diameter of the bolt. Now, we generally express the bolt in terms of nominal diameter. So, hence calculate the nominal diameter. So, that is dB equal to dCb by 0.84, which is equal to 11.94. We can call it as 12 mm. Now, move on to the last component, that is big end cap, thickness of the big end cap. Already we discussed on the cap, the load acting is moment is acting, that is maximum bending moment we calculated as Fi x by 6. This is Fi x by 6, it comes from two different cases. So, first case, if it is a concentrated load, you will get one maximum bending moment equation. If it is a uniformly distributed load on the simply supported beam, you will get another equation. So, by taking an average, we get maximum bending moment on the cap is Fi x by 6. So, x is the distance between the bolt. So, distance between the bolt can be calculated as diameter of the crank pin or big end bearing plus 2 times of thickness of bearing liner plus nominal diameter of bolt plus clearance. Now, from here we can calculate that x equal to 65 mm. Maximum bending moment acting on the cap MC equal to Fi x by 6. Now, substitute Fi, that is initial force, already we calculated as 9490 and x we calculated here as 65 mm divided by 6. You get 102,810 Newton mm. Then section modulus, we take the cross section of the cap is rectangular, hence the section modulus Zc equal to BC TC square by 6, which is equal to 58 TC square by 6, which is equal to 9.7 TC square. Now, from here you can calculate the bending stress. The allowable bending stress is equal to 80 megapascal. So, 80 equal to MC by Zc. If you substitute this, you will get TC value. So, TC is found as 11.5 mm. 11.5 mm. Now, we find all the dimensions, but we have to check whether the induced bending stress is equal to the whipping stress or not, or is less than the whipping stress or not, so that our design will be, we can ensure our design is safe or not. So, now for finding the whipping stress, let us calculate the mass of the connecting rod per meter length. So, M1 equal to volume into density. So, volume is area into length into density. Already we know what is area, that is 11 T square, into length, that is equivalent length, that is 380 mm, and then rho density is given in the question as 8,000 kilogram per meter cube. Now, maximum bending moment M max equal to m omega square r into 1 by 9 root 3. Substitute mass value, omega value, r value, you will get 51.3 Newton meter. Now, section modulus Zxx equal to Ixx by 5t by 2. Now from here you can calculate the section modulus as 4792 mm cube. Now calculate the bending stress or whipping stress M max by Zxx, which you get 10.7 Newton per mm square. This stress, whatever the stress induced during whipping action, is well within the limit of 80 mm, that is allowable limit. So the design is completely safe. So in this connecting rod, we have to understand few points. First one, there are two forces. First force due to gas pressure. The second force due to inertial force of the reciprocating parts. Then we are designing 4 different parts. First one, we are designing the cross section of the connecting rod, and second one, we are designing the crank pin and piston pin. These two components we are designing with respect to gas force, because the induced stress is because of gas force. The third and fourth parts, the third part is a bolt which secure the cap into the big end of the connecting rod, and fourth part we have a thickness of the big end cap. So these two parts affects due to inertial force due to reciprocating parts. So hence these two parts must be designed with respect to inertial force due to reciprocating parts. So these are the important points. I hope we will see in the next video. Thank you.